Why models? Why would we use models in this space? Apologies to Aldous Huxley, but there are things are known in between other models. They're a great way of going from things you know to things that you would like to know but don't quite know, if there's some kind of logical link between those two things. Our program is going to essentially has two arms. One arm is integrating existing knowledge about polyphagous shothole borer to find out things that we would like to know. And the other one is making use of DPIRD's extensive data set, ideally, to draw new information out of that data set. So a combination of integrating things that are already known and then using data to learn things that we don't already know. So the first arm, integration of existing knowledge, this will all become clearer as we go along. Here's some existing knowledge, right? We know about the life cycle of this organism. There's been a whole bunch of lab studies that have looked at how fast individuals grow and how that changes as a function of temperature. There's a whole bunch of existing knowledge that we can put together to build not just a model of beetle growth, but a model of population growth for the beetle. And so we can use a model, we can use all this existing information that's out there, we can use existing information on daily temperatures anywhere in Australia that have been put together by whole thousands of people over the years. And we can build models of population growth that for polyphagous shothole borer, that we can apply to any place in Australia. And so here's some early examples of some of the work that comes out. This is the model run at Kings Park, right? So using the daily temperatures over a decade at Kings Park, and you can see this growth rate that dips during winter, comes up during summer. Running this model was, I would say, sobering. You can start with one beetle, and by the end of the year, you'll have more than 1 million, right? So this population grows incredibly fast. That's one of the things that comes out of this. Even though the beetle doesn't move very far, so on the order of hundreds of metres, the fact that the population grows so fast means that the population spreads at kilometres per year, right? So if it takes you 6 months to deal with an infestation, the invasion's already a kilometre past you by the time you've actually dealt with. So these are sobering facts that have come out of some simple integration of existing knowledge that was there before polyphagous shothole borer turned up in Perth. Another random little observation that we made from population modelling was that if you can get the dispersal mortality above 40%, the population will collapse, right? So the work on attractants and so forth that's being done, if we can come up with an attractant that works really well, potentially here's a way of actually controlling the population. And this is just information that's come from integrating existing knowledge through modelling frameworks to work out things that we would actually like to know: population growth, spread rate, and the population dynamics. We also learn, of course, about spatial variation in the growth rate of the population. So we can see that Perth's an okay place for polyphagous shothole borer in terms of temperatures. You go north, it gets a bit better. You go south, it gets a bit worse. We can extend this to the whole of the country. And this is work that my postdoc Andy Coates has done over the last 6 months or so. Basically, the takeaway from this is that if I was sitting in Cairns right now, I would be very, very concerned about polyphagous shothole borer and what's happening in Perth, because Cairns looks like the perfect place in the world for polyphagous shothole borer in terms of temperature. And there's certainly a big suite of potential host species up there in Cairns as well. So Andy's trimmed this. So this is thermal. This is the growth rate that would occur if that beetle was there and it was in a suitable host, right? Clearly, there's not trees in large parts of Australia, so we can cut those parts out, and we can start to build, and we can increase that mortality rate that I talked about before, and we can start to build something that looks like a species distribution model for this beetle. And once again, you can see that Perth's kind of an okay place for it. It's not the best place in Australia. There are going to be much better places in Australia for it than Perth. So the rest of Australia should be watching very carefully what happens here. Second arm of the project, this idea of drawing knowledge from new data. I haven't got examples here. So what I should have said before was that we will extend that population model into a spread model as part of this project. This next arm of the project is more about drawing information from the existing data. We don't have access to the DPIRD data just yet, but we do have access. Well, we've been working with DPIRD for the last 12 months on a different response, red dwarf honeybee, and so I can give you a sense of we can draw from those data that can be useful for management. So here's a response that DPIRD's working on in Northern Australia. They're doing a great job of eradicating this invasive pest that has arrived. One of the first things we can draw out of this response data is the detection probability, right? So this is the probability that you will observe the thing if it's there. And it turns out the vast majority of the surveys that DPIRD have been doing sit around about 1%, 1 to 3%. So if the thing is there, you've got a 1% chance of seeing it, which is tiny. And that means you need to do an awful lot of surveys, which is what DPIRD has been doing very successfully. But there are conditions, there are times and places when you can get that detection probability up to 75%. If you go there in September, you go somewhere where there's water and flowers, your detection probability is closer to 75%. So you can get a 70-fold increase in detection probability by choosing how to do your surveys, right? So this is really important information for designing surveillance. You can take this information about detection probability, you can combine it with the distance that we know that these bees forage, and you can move from a situation. So these black dots are surveys that DPIRD staff have done for bees. What they want to actually find, though, is the colonies, because it's the colonies that they're trying to eradicate, right? If you can eradicate the colonies, you've eradicated the bees. The surveys are for bees. And so by going from a thing that you know, which is the presence and absence of bees at a location, we're trying to make inference about where the colonies are. And it's possible to do this. It's a little bit like black magic, but you end up with estimates of how many colonies are left and where they are in the landscape. And that, of course, makes it really helps the response team to find the colonies that they're looking for eradication. So these are the kind of things that we can do with these data. With polyphagous shothole borer, we can certainly come up with detection functions that will enable people to optimise surveillance. So when to look, where to look, and which methods to use. That translates directly into how much surveillance effort do you need to put in to be sure that the thing is not there, or to be sure that you have eradicated it. So these are really important numbers to learn from the data. On the occupancy side, we can also learn what tree species they prefer the most, taking into account this detection probability issue. And we can also get into the nuances of, for example, which tree species. So some tree species might be susceptible in some areas, but not in others, right? So we can really drill down into the details of which tree species are most affected and what environments they're most affected in, right? So we can start to get some very nuanced information that I think will be really really important going forward for management and for working out what needs to be planted next and so forth. So the data that DPIRD have collected can really be used to step up our capability for managing this pest going forward. Once we've done all that, there's this kind of second chance for integration, right? So these other WARC projects that you've heard about are going to be running parallel to all of this effort. There's going to be new knowledge that are coming from these projects. It's going to be, you've just seen Paul's work, Trina's work, Theo's work. There's going to be all sorts of new knowledge coming from there, also from the DPIRD data. There's a chance to integrate all of that back into things like population models, and then we can do stuff like scenario testing, new surveillance methods, new control methods, and so forth, to ask the question in 3 years' time, is it possible that we might be able to step back into a different setting or not? Sorry. So the outcomes we're looking for from the modelling project are to optimise surveillance, where, when, and how we do surveillance. Predicted impacts, where they're likely to be, when they're likely to happen, which species they're likely to be affected, and then do scenario testing on what if we tried this, what if we rolled this new method out across space, what if we did it in this place and this time. So we can do all sorts of scenario testing on the new information that comes through. More generally, though, I think this WARC model is really important because it's starting to build the relationships and the collaborations that West Australia needs to deal with future pests, not just polyphagous shothole borer. There are more pests coming, and they will continue to surprise us. I've lived in just about every state in Australia at this point in my life. It's been very confusing. But I've noticed that West Australia has one of the best bushfire responses of any other state. A puff of smoke goes up in a bit of bush, and within 10 minutes, there's a spotter plane up there. Within half an hour, there's water bombers dumping water on it and putting the fire out. It's amazing. And we know that that's really important. Speed is really, really important for dealing with bushfires. It's exactly the same with invasions. DPIRD does that job, and they do it really, really well currently. But DPIRD's got a much more complicated job than bushfires, because every fire that DPIRD deals with is a different colour, and it has a different behaviour, and it has different methods for dealing with it, right? So DPIRD are really good, for example, at dealing with Q-fly, European wasp. In those cases, they essentially have the equivalence of spotter planes and water bombers. They can go out and deal with it. Polyphagus shothole borer was more like the equivalent of sending a bunch of people out with buckets and with blindfolds on to try and solve a problem, right? They desperately needed new tools, and it's taken us quite a while to get to the point where we might be able to develop those new tools. I think the kind of relationships and the kind of collaborations that are going to be built out of this WARC project are incredibly important, because they'll enable agile relationships and a real ability for the state to pivot towards research and development in a hurry when it's necessary. So I think that's possibly one of the biggest and most important legacies that might come from this WARC effort. So I certainly thanks WARC for making that happen. That's it. I'm done.